member of the OptimTex project team developed within the Erasmus program. It is my pleasure to open the third day of the Intensive Study Program with a practical work with a theme experimental design. This module will be sustained by manager of the project, Razvan Radulescu. I would like to underline that after the practical activity presentation, but also during it, especially students have the opportunity to ask questions in order to better understand the information received. Please take this opportunity. I wish both to teachers and students a fruitful and useful day. Razvan, is your turn, please.
Yes, so Mrs. Visilanu, many thanks for this kind introduction. With your permission, we are going to study today the practical work of the module Design of Experiments. So I would like to share my screen at this moment and to start today's lecture. First of all, I would like to ask you if you had the time to take a look at the Moodle platform at the course, and if you have any questions prepared for today's practical work. And I would also like to tell you that we have prepared for today's lecture a much more simple example in the field of design of experiments, namely factorial plan with two parameters, which should highlight you in a most simple way the meaning and the concept of this design of experiments. So now I would like to tell you the summary of our today's lecture. We have first of all a brief explanation of the rationale of design of experiments. Why do we use this statistic branch? Why is it useful? Then we will present this simple example of factorial plans with two parameters for educational purposes. So we have selected the most simple plan for you in order you to get the concept of experimental design. Then we will compute the factors of the polynomic equation in Excel by regression. Afterwards, we will decode the coefficients and compute the polynomic equation. We will see also an example on how to plot in Matlab the surface response. And moreover, we will also have some design of experiments in Modde, which is a specialized software for experimental design, which is proprietary, but it has also much more features in this field. So it is a specialized software for design of experiments. Well, regarding the rationale and the context of design of experiments, why do we need design of experiments in our life, in our research? Well, mathematical statistic methods and optimization methods are used for a rational selection of experimental determinations in order to obtain a feasible and coherent insight of data. What does this mean? That we envisage a reduction of the experimental determination to a strict minimum. So we want to reduce the number of experimental determinations, which means costs, times, and financial resources, which we can save if we reduce this number of experimental determinations. Now, regarding a simple plan, this is the factorial plan with two parameters. we can see in this slide that we have the input parameter A and the input parameter B. Then we have an experimental process, and then we get a result variable. And in order to showcase you this simple example, we have used an example of a pill which is manufactured by a pharmaceutical company for vitamin C. And this is a most simple example. It is not in the textile field, it is in the pharmaceutical field. However, it showcases these factorial plans with two parameters. And what is the concept? We have firstly parameter A, which is the concentration of particles in this pill of vitamin C. The second parameter B is the dimension of these particles within the pill. And then we have this manufacturing process, and the result variable is the release time of these particles in our body. Yes, so this is the release time and the result variable measured in seconds. Now, here is a very important slide. You should focus on these explanations now, because now we are explaining what is the concept of this factorial plan. First of all, we have to acknowledge that we have two variables, the concentration of particles and the dimension of particles, which vary at the same time, so they vary simultaneously. We have not a single parameter, we have two parameters, and we can also analyze the interactions between the two parameters. And now we have selected for this dimension of particles, according to preliminary research, two values, 60 micrometers and 80 micrometers. For the concentration of particles, we have also two percentages, 1% and 2% of active substance for vitamin C. And now we would like to analyze within simple factorial plans the interconnections and the combinations of these two parameters. And in order to be able to make the interconnections between these two parameters, we have to encode these parameters. What does this mean? We have to have an upper value, which is +1, and the lower value, which is -1. So 80 micrometers is the upper value with +1, and 60 micrometers is the lower value with -1. As well, for the concentration of particles, the 1% is the lower value with -1, and the 2% is the upper value with +1. How did we obtain these encoded variables? By this relation. So S, if we compute, is the value V, let's say 80, minus the mean value, which is 70. So the mean between 60 and 80. So 80 minus 70 divided by delta, which is 10, gives +1, which is 80. 60 minus 70 divided to 10, which is this difference between 70 and 60, gives -1. And as such, we can see here these two relations for encoding the concentration of the particles, which is C minus the mean between 1 and 2, which is 1.5, divided by the difference between 1.5 and 1, which is 0.5. So difference between 1 and 1.5. Well, so these are the two encoded variables as such as we get for the upper and lower value +1 and -1. Now, why do we do this encoding? Why is this encoding useful and why do we use it? We use it for afterwards, we have to define this experimental matrix. We have here the number of the experimental run from 1 to 4. And then we have all these combinations between the upper value and the lower value for both factors, for factor X and for factor Y. Factor X stands for concentration and factor Y stands for dimension. And you can see on these two columns, we have all combinations between -1 and +1 of the two factors. And we did this encoding because we would also like to have the interaction between X and Y. And for this interaction, we have multiplied -1 with -1 gives +1. +1 -1 -1 and +1 and +1 gives +1. And this is our experimental matrix. And on the last column, we have the result variable, which is the release time in seconds. So this is the result variable. And we have measured values in seconds here. As you can observe, for a greater concentration of particles, for the upper value of for concentration of particles, from the upper value of dimension of particles, we have the greatest release time. Well, after this step, we have to associate a polynomic equation, first degree, which is this, which has this form. So we have intercept, which is A0. We have a coefficient for X. We have a coefficient for Y. And we have a coefficient for the interaction between the two variables, which is A3. How do we compute these values, these regression values? Well, in order to compute them, we can use Excel. And you can see on this slide, we have to simple copy-paste this experimental matrix on a worksheet in Excel. You can see this here on this left part of the screen. And then we have to select data analysis from the data tab and to select regression. One important remark is that for this data analysis to be installed, we should install the add-in data analysis from the option tab of the Excel software. So if you don't have in your Excel software this option of data analysis, you should know that you have to install this add-in from options. Well, and afterwards, if we introduce in this Excel software these parameters, we obtain here in the bottom part of this slide the coefficients for A0, which is the intercept, for the encoded concentration variable, for the encoded dimension variable, and for the interaction between the two variables. You can see here on the second column the coefficients computed by regression in Excel. Well, and now on the upper equation, we can see that we have introduced these coefficients computed by Excel in this equation. This is a polynomic equation first degree. And we have introduced here all these figures computed here by Excel. So 73.75 is the intercept, and we have introduced this here. Now, we have to remember that we have used an encoding for X and Y related to the concentration and the dimension accordingly to these two equations from the previous slide. In order to get a polynomic equation which represents this result variable of release time in seconds, we have to introduce in these first equations the X in this equation and the Y, and to compute slowly without errors. This is quite challenging computing. This second equation, which is depending on C, the concentration, and D, the dimension. You can also see that we have for this interconnection between these two parameters also a coefficient which is 0.25, which means that there is an interconnection between the two parameters, concentration and dimension. Afterwards, we are going to plot our equation, which is given here by this Matlab formula in Matlab, and we have defined for this purpose an interval of values here for the concentration from 0% to 4% with 0.1 step. This means 40 values. And for the dimension between 50 micrometers and 90 micrometers with a step of 1 micrometer, which means also 40 values. Now, we have defined an area of these vectors, and we have subsequently introduced this formula we have computed, and we have used the surf function of Matlab depending on these three variables, and we got this response surface area. Well, what insight have we received by this procedure? First of all, we can observe that the greater the concentration is, the greater the release time, and as well the greater the dimension of particle, the greater the release time. And that there is an interaction between the two input parameters, concentration and dimension, with a coefficient of minus 0.25. Now, this was a most simple example, and the insight is not so complex at this moment because we had only two parameters and only two variation levels. Now, with your permission, I would like to ask you if you have any questions up to this moment, if you have understood this example, because we would like to move forward, and we have to be sure that you have understood this first example.
Would you like to repeat something?
Well, if not, we are going to make now some practical examples. First of all, we would like to make this regression in Excel. So I'm going to this slide. I'm going to the experimental matrix, and I will copy these values for factor X, factor Y, the interaction factor X multiplied by Y, and the result. So I'm going to copy these values. Now I'm going to share the screen and to share the screen with Excel. Yes, so now I'm sharing my screen once again with Excel software. Well, and now I hope you can see this worksheet in Excel. I can copy paste these values in an Excel sheet. All right. And then I write here that this is variable X, this is variable Y, this is variable Z, the result, no, this is the interaction X, Y, and this is the result variable Z. And now we select from data this data analysis. And we have here several options for statistic methods, and we will choose regression. Now, for the Y range, we will introduce the result variable, and we will select these fields, 55, 70, 80, and 90. For the X range, we will introduce this matrix of X and the interaction between the two variables. So the -1 and +1. And then we write OK. And as you can see on this sheet, we have got these coefficients on this column of this regression computing for our polynomic equation. Now, as said, these coefficients are important for computing these polynomic equations with encoded variables, and then we decode the variables. Now, with your permission, I would like to also show you this plotting in Matlab. So now I have once again unshared my screen, and now I will share the screen with Matlab, which is once again a software which is proprietary. So this software is not for free, but it has a 30-time trial period. So if you would like to use this software, you have a 30 days trial period to use it. One question, do you use Matlab in your studies? So are you familiar with this software? Please, feedback from one of the students.
Not really.
Not really, yes?
Yeah, I use EGLab, which is an extension of the Matlab.
Yes, so you use an extension of Matlab in which extension?
It's EGLab, which is used to analyze EEG signals.
Ah, yes. All right. So this is the basic module of Matlab with no extensions, only the standard version. And as you can see, I have copy-pasted my small program here with the two variables, C for concentration, D for dimension, and the mesh grid which gives us an array. Then this equation for Z, which on which we have computed all these coefficients here after decoding the coefficients from Excel. And then I put here this surf Matlab function with 3 parameters. And then I have also set a label for each coordinate. Then I can write here in the command window the function experimental design 1, and I hope you can see this new window with surface plot. Can you see it? I don't know if WebEx has the possibility to see this second window. Can you see this Matlab figure?
Yes.
So yes, all right. So you can see that we have on this axis the concentration we had as values 1% and 2%. And here we have the dimension with 60 micrometers and 80 micrometers. And here is the surface plot. Well, any questions up to now? We are going further, and we would like to be sure you have got a main idea of this experimental design, because the examples we have presented yesterday are more complex. They are dedicated to the textile field. However, in order to understand the examples of yesterday's lecture, we have to clearly understand these principles of design of experiments. Are there any questions up to now? Did you get this feature of varying two parameters important for a research process and this result variable? Well, all right. Then I would also like to present you another software, because our project is related to software for experimental design, which is dedicated for design of experiments. So this is a dedicated software. It is called Modde. It is also not free. It is not open source. However, it has also a trial period of 30 days. And this Modde software is specialized in design of experiments. Now, with your permission, I will share this screen once again with this Modde software. So here we have this Modde software, and here we have, for instance, the two factors of our small example, the concentration and the dimension. In order to use this software, we have here a design wizard, which is located on the left upper part of the software. And in this design wizard, we have firstly to introduce the input parameters or the factors. First factor is concentration, and it has the abbreviation con, and the measurement units is %. Second factor is the dimension with abbreviation dim and unit micrometers. Then we have to define the responses, which is the release time, the with abbreviation RL, and the units in seconds. And then the software performs automatically this experimental matrix, in which you can see these numbers -1, +1 for concentration, and the -1 and +1 for dimension. You can see all possible combinations between -1 and +1. This is 2 at power 2. This means 4 combinations are available in this software. Moreover, this software requires also 3 middle points, which are with 0 for a better evaluation of the analysis. And we have introduced here in the last column all these values for the release time regarding the concentration and dimension. And as you remember, we have 55 seconds for -1 and -1, 70 seconds, 80 seconds, and 90 seconds. As long as we have introduced this data, we have the possibility to provide this surface plot in Modde. And we access this contour option, and we have this surface function here, which is automatically, and we can see on the screen quite similar plot as in Matlab. you can see here on this axis the concentration, on this another axis the dimension, and here you can see this surface plot for the release time. Well, this is regarding Modde, so another software used to compute experimental design. And now, with your permission, I would like to come back once again to this PowerPoint from yesterday, which which tackles these examples from the textile field. Yes, so we have also examples in the textile field, and we would like to show you once again what these more complex examples of design of experiments are. So now I will share once again my screen. You remember this PowerPoint from yesterday. I will not come back to all details. However, I will jump directly to these examples of factorial plans with 2 parameters and 3 variation levels. You can see here on this slide that we had for this plasma treatment of fabrics for hydrophobic functionalization 2 independent variables, and one is the power of the plasma generator. So the plasma installations is an installation with several parameters to install, with several options, yes. And one of the options is to set this power of the generator. And the second important parameter is the process time. So we can treat in plasma fabric for 10 seconds, for 20 seconds, for 1 minute, for 5 minutes. But depending on this process time, the result on the fabric, on the hydrophobization of the fabric is different. So we have different results by different parameters. And our aim is to see what is the most optimal, so what is the optimal parameters for the maximum hydrophobic functionality, which is measured by this water contact angle. The water contact angle is a measure of hydrophobic functionality of a fabric, and it is measured by the angle formed of a droplet of water on the fabric surface. If the angle is high, if the droplet stays on the surface, then the fabric is hydrophobic. If the droplet has a low angle and if it is absorbed by the fabric surface, then it has a hydrophilic or not hydrophobic character. Now, we had for our experimental plan 3 variation levels. You can see on this slide that we have 30 watt for the power as the upper value. We have 10 watt for the generator power as the lower value, but we have also a medium value, which is 20 watt. Regarding the process time, we have 4 minutes for the upper value and 2 minutes for the lower value. And we have also this delta, which is the difference between 20 and 10. And here we have delta 1, which is the difference between 3 and 2. Now, the experimental matrix is as such. You can see here on this slide that that we have here this encoded variables, the power with all possible combinations of 1, 0, and -1, the time with all possible combinations of 1, 0, and -1, then the interaction between the 2 variables, x multiplied by 1, and you can see here it corresponds to this multiplication. So 1 multiplied by 1 is 1. 1 multiplied by 0 is 0, and so on. Then we have here another option. We have a polynomic equation second degree, because you have more values, and this experimental matrix allows us to propose a polynomic equation second degree. And we have here x to power 2 and y to power 2, and we see that it corresponds that is minus 1 to power 2 is 1 and minus 1 to power 2 is 1. So, and on the last column we have the result variable, which is the contact angle in degrees. Yes, so we have here degrees, 138.3 degrees. This is the angle. All right. And we have also encoded our variables accordingly to these two expressions. X is p the power minus 20, which is the mean, divided by 10, which is delta, the difference, and the time, which is t minus 3, the mean value, divided by 1. And here is this polynomic equation. Then we have computed the regression in Excel as shown. Here are the coefficients computed. Here we have decoded the coefficients of the polynomic equations, and we have expressed them in the bottom part of equations power and time, and the result is the water contact angle depending on power and time. And then we have plotted once again in Matlab the response surface of these equations after computing these coefficients. Well, we hope that this practical work could open you the concept of this design of experiments, which is, as said, a branch of statistics meant to optimize the number of experimental runs in a research project. Now, if there are any questions, we are ready to answer and to provide you feedback.
Any case, Razvan, these examples are very useful in our research activity. Very good.
Yes, many thanks, Mrs. Viciliano. Indeed, yes. Such examples are used in experimental work, in experimental research. And we hope for your future studies, it will be a lot of support to know some basic concepts of this design of experiment. You can see there are also many papers in the scientific literature which use design of experiments of different degrees of complexity, and which have applications also in textile finishing or other applications in textiles. Null applications, yes.